Hello everyone, my name is Samir Kumar Singh. Today we will discuss a week 11 tutorial, and this week I decided to do some MATLAB programs that are basics code. It will help you to make your concept of more strong. So firstly we will discuss the MATLAB code for the relay channel. Here we will see how we can generate on this on the MATLAB. Okay, because some students says that we have to do some MATLAB programming. Okay, so firstly, these three are the basic command. CLC close all clear all generally we are used. Basically, it is used for the clear the command window. That is the close all is used for the close all figures. And third is the clear all. It is used to clear the workspace. Okay. Basically, relay channel. Relay channel is used to represent the non-dominant and sorry to represent an OS channels. Okay. So basically, so how we generate it? So basically we have taken and this is the number of terms, and this is the very high, it is 10 to about 6. Okay, firstly we have to generate the h is known as a channel. Okay, so for the channel we just to show the random nature we have used the random 1 plus n. This part show the real numbers, and that is the that part show the imaginary numbers. So for on the large scales we take the 10 to power 6 terms of the real parts and imaginary part when we do the summation of that, and for the then it will follow the channel relay channel. Okay, so it's the 1 upon square t upon 2. Okay, and that shows the variance. Basically it have a mean 0 and variance. Total variance is 1, real part having the variance 1.2 and imaginary part also having the variance 1 by 2. Next we will do, firstly here we are showing the amplitude of the channel amplitude. So we take the ABS, and next is the angle. To show the angle we take the angle of the h. So we have we have to plot the PDF of the amplitude and PDF of the amplitude and PDF of the angle. So firstly we find the amplitude and angle. This represent the x-axis. So so the PDF we plotted the histogram. Okay, this is the amplitude and this is the x-axis. Okay, this is the amplitude. So by doing this we can plot the amplitude of the PDF, and similarly for the angle we did the same. And so that is the basically a result of the amplitude PDF, and that is the PDF of the face. Okay, so we will do it in MATLAB. So same code is written there, we just run it, and you can see that there you are getting your amplitude. This curve showing the amplitude, and this is the phase. And now if we change the value of n for the short span, here we are taking out 10 to power 6. Okay, now if we take it for the 10 to for the 100 terms only. Okay, so it's okay, so that is not following the relay, it's showing like that. Okay, so to calculate this we have to take the large numbers. So it will look like this. Okay, this is the amplitude. Basically relay channel look like this, and this is the phase. Okay, if anybody have doubt can ask. This is a basic command. Okay, this is a workspace, that is a command window. So clear the workspace we use the clear all, and clear the command window we use the CLC, and close all use for the close all figure. Okay, that is the basic code. And next we consider the next we calculate the BR of the relay channel. Firstly in the first program we generated the relay channel, next we are calculating the BR of the relay. Okay, so what is the concept behind it? Here we plot the VR with respect to SNR. Okay, So basically the first three command is a common. Next here we are varying our SNR, that is in dB. It's going from a 1 to 13. Okay, this basically this is representing our bits, total number of bits. Their block size is hundreds and number of blocks it's it okay 10,000. Okay, next we generated the matrix that having the zeros first in the VER, and the size of the matrix is the depending on the SNR dB size. Simply we again we generated one matrix at this is the in this term. Okay, now we have a block size of the 100. Okay, we have to generate a bit and it should be in the form of the 0 and 1. Okay, so by using the randi function we can generate it randi 0 1, and it's going from the size of the this bit 1 comma block size. Okay, so there we will get our bits. Now firstly we generate a channel. For the channel we are doing the same thing, 1 upon xqrt2 random plus j into random. This showing real parts and that is the imaginary. Okay, so new thing is that here we will generate our noise. Okay, that's following the AWGN noise. Okay, so for this we using this function that will show that will present our noise. Okay, so we have the value from the 1 to 23. So firstly we calculate the one, next three as some like that. So firstly we calculated the we'll be running this loop from the 1 to size of the length of the SNR dB. This is in dB. Then we calculate in the linear scales, so it will look like that. Okay, so now we have the input messages. Now we'll transmit the transmitted message. What will we transmit with the power and the input bits that will be represented by these equations, and the receiver end we know that y is in the receiver end we represent it as y, so it's become y is equal to x h into x into n. Okay, x is the transmitted message, we already calculated this, and that's second is the noise and this is the noise. So on the receiver end we will get hx plus n. Now for the next term is that it process bit. Here we will multiply it with the conjugate of h with the received messages. Okay, so there we will get process bit. Now we will decode at the receiver end. So for the threshold we consider real part of the process bit, and if it's greater than equal to 0, this is the threshold. Okay, so yeah, from there we will get a real we will calculate decoded messages. If our real parts comes greater than 0 equal to 1, so we consider this one, otherwise we will take it as a 0. Okay, now we will calculate number VER. So VER initially it's stored in the form k, and we compare our decoded bits the transmitted with the initial bits. Okay, so if it's equal then it's called 0, if it's not equal it will give 1, and that will become our VER. So total VER rate, total there we go to VER, so it will be calculated VER and total number of the bits, that is the number of blocks, and into multiplication with the block size. From there we will get our VER, and we will plot it in the semi-loggy. So firstly this is the simulated curve, and there for the next we are using the just directly formula, and it's a 1 minus xqrt SNR of linear upon 2 plus SNR. It's a direct formula to calculate the VER of the relay channel. Okay, so we will check it by the result our code is right or wrong. So when you plot, that is the steps. Okay, we are already I discussed that with you, so it will become like that. Okay, so here you can see that your simulated and theory simulated and formulated curve with the both the same. It means your code is right. Okay, for the demo you can see that on there code the same as I wrote on the wrote on the PPT slides, but we just run it, and the curve is coming same. Basically This is a direct formula of the to calculate the BER of the relay channel. Okay, and that is our simulated BER. Okay, next we will calculate the BER of the selection diversity. Okay, as we have schemes that we have learned few diversity schemes like MRC, GCSE. So firstly we will consider take it up as SC diversity schemes. Okay, so we will calculate here the BER. For the reference you can use the previous code. It will help you to make the code of this diversity scheme. Okay, so pattern is the same. Firstly we generated input bits in form of +1, -1, and X channel and the noise, because we have the Y is equal to HX plus 1. So we will generate H and add our input bit. Okay, next multiply the bits with the channel and add noise. In this form we will do it in the MATLAB. For the especially in the selection diversity, we choose the maximum power path. Suppose you have a one antenna transmitter and two receiver end. So we have you have a two path. You will select the maximum. So and then on the receiver end, select the receiver path with the maximum power. Basically for forward scenario, we have one transmitter and two receiver. So we will select the receiver part which having the maximum power, and apply the next we apply the equalization on the receiver symbols with the known channel. After applying the equalization, we perform the same hard decision decoding techniques and count the bit error rates. And next last step is the repeat this step for the multiple SNR values and plot the simulated result. These are a few steps. We will follow it and try to generate the BER of the diversity schemes. Okay, so this is the code of the BER of the selection diversity. First three line mostly as common. Okay, next is the n is equal to number of bits or symbols. Okay, so first task our first task is the generate the bits, channel, and wide Gaussian noise. So we firstly focus on these three terms. Okay, so firstly we will generate our input bits. So by using the rand function, we can calculate that it will come in the form of 0 and 1, and it will total number of bits will be 10 to the power 6. And next, what is the task? We have to generate the bits in form of -1 and 1. So for that we will apply these equations. 2 into input bit -1. If you put the 0, this will become 1. If you put the 1, it will become, sorry, here we will get your input bits in form of 0 and 1. Just put it. You will get a, when you put 0, it will become 1. When you put the minus, when you put the 1, it will become, okay. Using them by using the BPSK modulation, we can calculate it. Next, for this scenario, we consider that we have on the receiver end we have 2 antennas, and there we will value our SNR from 0 to 35. Okay, so here we will learn our loop for the two antennas, because we have to add the receiver and we have 2 antennas. Okay, half code is there. Next half portion is discussed on next slide. Okay, so this code firstly we run for 2 antennas. So we consider the length of the receiver antenna there. Next, for the particular SNR values, so we consider 2 loops. Okay, next task over to generate a noise and the channel. Okay, so here we will generate our noise. Okay, so it's the same as where receiver antenna is the 2. So for both we generate a noise, and similarly we generate a channel the relay. It will look like that. Okay, 1 upon XQRT receiver antenna and n number of bits. So from there we can calculate the noise and H. Okay, this is the cron function is used to arrange the matrix in proper format. Okay, from there from the steps we get the X, H, and N So now we will calculate the y. Y is the equal to y hx plus n. Okay, so it will look like that. Now we will calculate what for this function. We find the power of the channel for all receivable channels. So we multiply the conjugate h with the h, so it will become give the power. So from there we get the maximum power. We will find the power. Next we will get the maximum power by using these two functions. Okay, and selecting the chain with the maximum power, because we get the matrix. Now we'll choose the which one having the maximum power. Okay, y. This is our selection diversity techniques. Y SCL, SSCL. Okay, here we apply the equalization. Okay, and did the reshaping. So from there we will get the y hat. And next on the receiver end, we applied the hard decoding techniques. Then become your threshold value is the 0. From there we can get our input v hat, and that is the transmitted bits. Okay, so we compare with these two values, and from there we can count the errors, and this loop is end. From there we can calculate the BER for the simulated function, and it will become an ER upon n, and total bit it's the calculated number of errors. Okay, so now we will plot the result. So we calculated the EV and not ratio in the linear function. Okay, because SNR is given a dB, so we consider the BER of the receiver one for the first antenna, and then the second antenna. Just for this we use the formulas. Okay, and next we will similarly next for the we calculated the BER, and for the first receiver 1 and receiver 2, that is simulated. Okay, so by using this we can calculate the BER of the. So result of this schemes is, sorry, okay, it's not there, so we will learn it. You'll see it in on the there. So this is the code of the selection diversity. We will learn it. PC is little slow. Again. Okay, once again. Okay, this is the curve of the selection diversity. Okay, by using the relay channel, and this is our for the two antennas scenarios. Okay, Black is the simulated and red is the simulated theoretical by using the formula. Similarly, it's for the one antenna. This is the advantage of the selection diversity schemes. Okay, so I will add this result on the PPT. Next, we will discuss the EGC diversity schemes. Okay, EGC known as the equal gain combining. So it's a little different from the EGC techniques. Okay, here we will, when we apply the equalization, we by using them, here we will using the concept. Here we will multiply with the channel phase. Okay, on the receiver end, apply equalization by using the known channel phase. And next, accumulate the equalized symbol for the all receiver parts. This is the principle behind the EGC diversity scheme. All techniques is the same. Firstly, we will generate the bits, input bits in form of the +1 and -1, then channel, and then white Gaussian noise. Next, multiply the bit with the channel and add noise in these terms. Okay, so from there it will seem like a SC techniques. What is the new? Then on the receiver end, apply equalization by using the known channel phase. Okay, so there we consider that the channel receiver on the receiver end it have a period information about the channel, so we will do the equalization by using known channel phase. Next, accumulate the equalized symbols for the all receiver parts. After that, perform hard decision decoding and decoding techniques and count the bit error rate. And after that, repeat this step for the multiple SNR values and plot the simulated result. Okay, the code is the same. First three commands. Next is the number of bits we will consider is the 10 to the power 6. Firstly, we will calculate the input bits. We generate the input bits. So by the rand function, it will come in the form of 0 and 1. But we using BPSK modulation, we want this in the -1 and the 1. Okay, so by using this, we will calculate this. And the scenario is same. Here we have it 1 transmitter antennas and 2 receiver antennas. Okay, so and EV or SNR values is vary from 0 to 35, and it's given in the dB. Okay, so next task is we have to generate the N and H. We will two times. We will use the looping 2 times. First for the 2 receiver antennas, and next for the SNR values that is varying from 0 to 35. Okay, so the length of the receiver antennas is the 2, and EV or TV this is 35. Okay, it's because it varies from 0 to 35. Okay, so we have firstly generated a noise, that is a white Gaussian noise, by using this function random NRX capital N, and similarly we generated the imaginary parts. That's the noise. On the same pattern we will use UV generator or relay channel. Okay, after that we will get our N and H. Next we will add them. We will multiply the add with the input bits and add with the noise. So by using the count function, we will balance size, and it's from there we will get at the Y or receiver receive bits. Now this is the new thing. Here we will apply the equal gain combining. So as we discussed, we divide the channel phase with the receive symbols. So it's when we divide, it's when we multiply, it's minus say come down on numerators. So we will apply the EG, we will multiply with the E minus J theta, and this is the angle of the H. Okay, so by using that, we removing the package of the channels. Okay, next we will build summation, adding values from the all receiver chans by this Y hat. Now applying the now we will do the hard decision decoding. Pattern is same, we compare with the 0. So okay, for using that we count the number of errors for the all SNR values. So it's will number of errors will become on this, we will store in on the NER function. Okay, so till now we will perform the hard decoding and count the bit errors rate now. Okay, next this is the stimulated. This is the plot. This is function are used for the plotting. Okay, this is the for the transmitter receiver antennas for 1, and it is the receiver antenna for 2. Okay, that is the formula that is using in the for the EGC to calculate the BER. That is the 1 by 2 minus 1 by under root EBL upon 2 EBL SNR plus 2 upon SNR plus 1. That is for receiver antenna 1s, and that is receiver antenna 2s, and that goes for the simulation functions. Okay, so from there we can plot this. So it will look like that. This is the for the relay. This is for the this EGC channel by using the EGC techniques for the DJ relay channel. This is the for the one cross one antennas, and that is for the 2. This is the advantage of the EGC schemes. Okay, now we'll see it in the MATLAB. Okay, code is the same. Okay, this is the curve. I think it's clear. So to calculate the BER, we will calculate we will generate our receive symbol. We firstly find the receive symbol at the receiver end. Okay, then we will compare with the thresholds and count okay, threshold values, and from there we can count the number of errors, and we will divide the number of errors with the total transmitted bits. From there we can calculate the BER. I think this 4 codes will help you out to calculate the BER for the any scenarios. Then what we will change, we will vary our receiver antennas, transmitter antennas, and we can there mostly we will use the 2 loops, and by using the same concept we can calculate the BER. That was the relay. Here we will, by using this we can generate our relay. This shows the real terms, and the imaginary terms. When you add in for the larger scale, it will follow the relay. Okay, so if anyone have doubt, please ask. Okay, again I am repeating, this is the code of relay BER. To see the pattern the same, we just generate a noise H input bits. Okay, we from the by using these 3 terms we calculate a y is equal to hx plus n, and multiply with the receiver with the conjugate of h. Okay, so already then I can apply the decoding, compare the process bit with the 0, set threshold values, and from there we calculate the BER. Selection type, this is a selection diversity codes, and that is for the EGC schemes.